Hey everyone, Victor is here, and in this video I want to talk about Lewis acids and bases. For the most part, whenever it comes to organic chemistry, we are going to be focusing on the Brønsted-Lowry theory. And the Brønsted-Lowry theory is all about the proton transfer. So like for instance, in the first example that I have here on the screen, the proton transfer is going to be between the OH and my protonated amine. So what I'm doing here, I am grabbing the proton, and that proton going to end up on my water, which is going to become a conjugate acid. Also, whenever we are dealing with Brønsted-Lowry acids and bases, we're talking about acid, base, and then their conjugates, the conjugate acid and conjugate base. However, in Lewis theory, it's all about the electron sharing, and we are going to be talking about complexation rather than proton transfer. So in Lewis theory, we are going to have a base, and that base is going to make a complex with an acid by making a new bond between the elements. So let's talk a little bit more about the Lewis acids and bases and what exactly those are. Lewis acid is the electron acceptor. So any species with an empty orbital that can accept electrons can be easily classified as a Lewis acid. So for instance, H+, a proton without any electrons, would be a Lewis acid. Or, let's say, a carbocation, like, for instance, a CH3+ species. Or boron-containing compounds, like, for instance, BH3, where boron has an empty orbital, which I will show as a little box, or something like BF3, which also has an empty orbital on that. We're also going to see Lewis acids that are going to have metals as a core, so something like, let's say, aluminum chloride, AlCl3, or iron bromide, FeBr3, or let's say titanium chloride, TiCl4, etc. So whenever we have a metal which can potentially accept electrons onto its d orbital, that can serve as a Lewis acid as well. On contrary, Lewis base is something that's going to be donating the electron density. So essentially anything with an electron pair can serve as a Lewis base. So we can have, let's say, H2O, water, being a Lewis base because it has electron pairs. On contrary, the Lewis base is going to be the donor of the electron pair. So any species with an electron pair can be serving as the Lewis base. So for instance, I have water with a couple of electron pairs, or I have an OH anion with 3 electron pairs, or ammonia with an electron pair, or some sort of alcohol with a couple of electron pairs, or chloride anion with 4, or even something like triphenylphosphine, which has an electron pair as well, so it can as well serve as the Lewis base because that can give electrons away. So as I've mentioned a moment ago, when it comes to the Lewis acid-base complexation reaction, we're essentially going to have two species that are going to be coming together to make one bigger molecule. So, for instance, let me illustrate it on the example. I have BF3, which is a good Lewis acid because it can accept electrons, and I have, let's say, a diethyl ether molecule over here, which can donate electron density and serve as a base. In this case, oxygen is going to give electron density to the boron, and what we are going to end up with as a result is a new boron-oxygen bond, where I have my boron still surrounded by all of my fluorines, like this, but now, because oxygen gave the electron density to make a new bond with boron, we're going to have a formal plus on the oxygen, and because boron has accepted the electron density, we're going to assign the formal minus to our boron, just like that. In this case, my acid is going to be boron trifluoride, so I'm going to say that this is my acid, and my base is going to be the species that gave the electron density to make a bond, thus it is my diethyl ether. The resulting species that I have over here is going to be my complex, and it doesn't have any other fancy name or anything of that sort. That's just some sort of a complex where two molecules came together to make one bigger molecule. Here is another example. Let's say I have a chlorine molecule, just a regular diatomic chlorine without anything else on it, and I'm going to react that with iron chloride, FeCl3. Since iron has an empty orbital which can accommodate more electrons, the chlorine in this case is going to donate those electrons towards the iron, which means that chlorine is going to be my base, while iron is going to be my acid. In this case, I'm going to make a new bond between chlorine and iron, so I'm going to write that bond, and of course I will still have the rest of my chlorines around my iron just like that. Now, because chlorine has given some electron density to iron to make a new bond, we are going to assign a formal plus onto chlorine atom, and iron, since it gained some electron density from chlorine, is going to have a formal minus on it, just like that. Occasionally, we're going to classify some other reactions like Lewis acids and bases as well, although it's not necessarily as often. So, for instance, I can have a reaction where I'm reacting a pyridine molecule, which looks like this, with, for instance, a formaldehyde molecule, which is going to be this molecule. When these two species react with each other, the formaldehyde does not necessarily have an empty orbital to accept the electron density, but we have a significant delta plus on the carbon, so carbon is what we would refer as an electrophile. It loves the extra electron density. So pyridine can donate that electron density onto a carbon, but in order to accommodate those electrons, carbon would have to push extra electron density via the pi bond onto the oxygen. Well, in this case, what we are going to end up seeing is the final product where we now have made a bond between nitrogen and carbon like this, and because we have pushed electrons onto the oxygen will have the formal negative on it, and nitrogen, because it was the source of the electron density in this case, going to end up with a formal positive charge like that. While this reaction is not our typical Lewis acid-base reaction, some instructors still do like to classify reactions like that as Lewis acids and bases rather than nucleophiles and electrophiles, so you might very well see something of that sort in your class. Remember, if in any kind of reaction you are given an electron density from one species to another species to make a new bond, you could potentially classify it as a Lewis acid-base reaction. So in this case, nitrogen is giving away electrons, which means that that is going to be a base, while carbon is accepting those electrons. It doesn't matter that the electrons moved within the molecule itself. What does matter is that my formaldehyde over here was the acceptor of the electron density overall, which means that that was my acid. And as I've mentioned, while it may not be necessarily the most common way to classify Lewis acids and bases, it does happen from time to time, so be prepared if something like that shows up on your test or homework. One other thing that I want to point out here, we don't estimate the equilibrium constants for these reactions like we did for Brønsted-Lowry acids and bases. Well, we don't really have those constants easily tabulated, and we cannot easily find them anywhere. However, we can deduce if one complex is more stable than the other complex using similar 5 factors that we have seen before when we were dealing with acids and bases for the Brønsted-Lowry theory. So, for example, let's look at these compounds. The nitrogen and oxygen containing compound can serve as our Lewis base because we have electron pairs on the nitrogen and we have electron pairs on the oxygen, and boron has an empty orbital, so boron can serve as the Lewis acid in this case. And since we have 2 potential places where the reaction can take place, either on the nitrogen or on the oxygen, we have 2 possible options for our products. Option number 1 is going to be if oxygen reacts with my boron. In this case, I'm going to end up with a molecule that looks like this. If, however, I have the other option where the nitrogen attacks boron, then I'm going to end up with option 2, in which my final complex looks something like that. Now, in order to assess which complex is more stable, I'm going to use the same 5 factors that I have used for the acid-base reactions when we were talking about the Brønsted-Lowry theory. So, as a quick reminder, my first factor is resonance. Generally speaking, resonance is a good factor regardless of what type of a charge I'm looking at. If my charge is stabilized by the resonance is going to be good for it, and the molecule is going to be more stable with that charge. Atomic size, well, that one kind of depends. When it comes to the Lewis acids and bases, the better the orbital overlap between the species, the more stable that species is going to be. So if you're trying to make a new bond between, let's say, two atoms of the same size or similar size, like let's say oxygen and boron or nitrogen and boron, they're all in the same period, so they're relatively similar in their size. In that case, the bond is going to be relatively strong simply because we are going to have a relatively good orbital overlap because the orbitals on those atoms are similar in size. But if I'm trying to make a bond between two elements of drastically different sizes, let's say if I'm trying to put a hydrogen atom on selenium atom or something like that, where the sizes are really different from each other, that is going to make what is known as a frustrated Lewis acid pair or frustrated Lewis acid complex, and those complexes are typically not very stable and will tend to decomplex or fall apart very easily. So in this case, it's not just about the size of the atom with the charge, but it's more about the size of both atoms that are making the bond, and the closer the sizes are, the better. The next factor was electronegativity, and generally speaking, since in many cases of Lewis acid-base complexes we are going to be making positive charge, if we are making a positive charge, then the lower the electronegativity of the atom with a positive charge, the better it is, the more stable it's going to be. When it comes to induction, generally speaking, the electron donating groups are going to be increasing the basicity of our Lewis bases, while the electron withdrawing groups will benefit the acids because they will pull the electron density towards themselves, making acids more hungry for electron density. Finally, the hybridization. When it comes to the availability of the electron pair, the ideal base is going to be sp3 hybridized, which is a little bit better than sp2 hybridized, which is better than sp hybridized bases. So your ideal base will have electron pair on the sp3 hybridized atom. So coming back to my two complexes that I have here, in the first case, I have the charge on the oxygen, so I'm going to highlight that oxygen over here. In the second case, I have a charge on the nitrogen, so I'm going to highlight my nitrogen as well. So if I go down my laundry list of factors, I can see that from the resonance perspective, there is no difference between my molecules. From the atomic size perspective, oxygen and nitrogen and boron, they are all in the same period of the periodic table, which means that size-wise they are roughly the same. Next, electronegativity. And here we do have difference, because oxygen has much higher electronegativity than nitrogen. Oxygen's electronegativity is roughly 3.5, while the nitrogen's electronegativity is roughly 3.0. So nitrogen with a positive charge is going to be way more stable than oxygen, which means that overall our green complex, our option number 2, is going to be more stable. Which means that if I were to perform this reaction in the laboratory, I would expect that option 2 would be my major product in this type of a reaction. And here is a useful trick. We can use our pKa table as the proxy for the stability of our complexes. So what I mean by that, let's look at exactly the same example that I've had on the previous page, where I have my starting material like that reacting with the Lewis acid, but now instead of the Lewis acid, I'm going to use H+ as my proxy, which technically is also a Lewis acid, but not the same one as we used before. So here I will have two options, two possible products. The option number 1, if I put the plus charge on my nitrogen by protonating that, I will have a product that looks something of that sort. If I protonate my oxygen, I will have the final product here looking like that, with a proton sitting on my O, and plus charge is going to be on the oxygen as well. Now, if I use my pKa table and I estimate the pKa values of these new species, I can see which one is more acidic, and by extension I will understand which one is more or less stable. So if I check my table and I look for an sp3 hybridized nitrogen, so I have nitrogen oxygen, it is sp3 hybridized, it has a positive charge, so the closest possible number for that in the pKa table is going to be somewhere around 10.5, 10.6 or so. If I look at my second molecule and I find something similar in the pKa table for that one, well, that is an oxygen that is also sp3 hybridized. It also has a positive charge, so probably it looks something like a protonated ether or a protonated alcohol in my pKa table, and those ones have a pKa value of somewhere around -2, give or take. Which means that when my oxygen is protonated, it's significantly more acidic, which means that it wants to get rid of that proton as much as possible, or significantly more than my nitrogen, which means that if my oxygen species is more acidic, it is less stable. Of course, you won't be able to use that trick for every single type of a Lewis acid-base reaction that you are going to see out there, but it can come very useful in many cases. So whenever you have species that resemble something that you have in your pKa table, once you protonate it, you can definitely use the pKa values as your proxy for what is more stable and what is less stable. We don't usually focus on Lewis acid bases in organic chemistry too much. However, that is still a very good idea for you to recognize those when we are talking about them and when you hear about Lewis acids and bases in your book or during the class discussion, because occasionally we will have to use Lewis acids and bases for certain reactions, although, as I said, it's not going to be all that often. Well, that's about it when it comes to Lewis acids and bases. Pretty simple, right? Leave me your questions and comments down below, and I will see you in the next video.